Welcome to build a real-time logistics tracker with Python and AWS. In this course, we are going to build a fleet management system from scratch using AWS and Python. This is one of the core technologies powering smarter logistics today. The course is organized into 8 sections. First, in sections 1 and 2, we'll cover the course goals and give you a high-level overview of the system architecture. Then, from sections 3 through 7, we'll build each individual component step by step. Finally, we will integrate these components to test and run the fully functional system together. Alright, let's get started with section 1. In this section, we'll go over the course goals and the learning roadmap. I'll also explain the overall system architecture and guide you through the initial setup, including creating your AWS account. First, let me show you a quick demo of the system we'll be building. You'll see a simulated truck moving on a map. The moment it enters a specific area, or geofence, the system detects it and immediately triggers a notification. Behind the scenes, this is powered by mapping data and AWS IoT services working together. Also, as an advanced module, we'll take it a step further. We will capture real GPS data from a smartphone and visualize its current location directly on a map application. In recent years, supply chain digitalization has become a massive global trend. In the logistics industry, this is about leveraging technology to solve complex challenges. While the scope of this modernization is broad, the goal is universal, tackling challenges like the explosion of e-commerce, rising operational costs, and the critical need for efficiency. Solutions range from basic cloud systems to full-scale automation and AI tools. In this course, we will focus on one critical solution, a real-time fleet management. We'll build the working prototypes together through hands-on practice and lectures. Let's break down the concept of fleet management. Here is a conceptual diagram. Imagine a map with a circular boundary. This is what we call a geofence. We also have a tracker, which is the moving object approaching that boundary. The tracker is equipped with an IoT device that transmits location data in real time. The geofence is defined by a specific center point and a radius. For our use case, imagine a truck approaching a factory warehouse. We can set a rule. If the truck comes within a 500-meter radius, send an automatic notification. Traditionally, a driver would have to call the factory staff and say, "I'm 10 minutes away." By using geofencing, we automate this entire process. This reduces waiting times and ensures that unloading and receiving operations run smoothly. Now, let's look at the overall system architecture. This system operates as a data pipeline. First, the truck sends the location data as the input. We use Python to handle the backend logic. Then, AWS Cloud Services receive this data, plot it on a map, and evaluate whether it has entered a specific area. Finally, we make this data useful for humans by displaying the tracker on a map or sending email notification. We will build this entire workflow using a serverless architecture. Here is how we implement this workflow on the AWS cloud. Since setting up physical IoT hardware on a real truck can be complicated and time-consuming, we will use CloudShell to run Python code. This code will simulate a truck by generating a location data. This location data is ingested by IoT Core, which is a managed service for connecting and managing IoT devices. For mapping, geofencing, and visualizing the tracker, we use Amazon Location Service. Think of this as AWS's equivalent to the Google Maps platform. Next, we use Amazon EventBridge to detect when the tracker enters the geofence. It then triggers Amazon SNS, Simple Notification Service, to send an email. SNS is a notification service that pushes messages to endpoints like email addresses or chat applications. Now, let me introduce the concept of serverless computing. First, let's review the standard cloud service models, SaaS, PaaS, and IaaS. SaaS, the software as a service, delivers a software application over the internet. PaaS, the platform as a service, provides a platform, including the OS and middleware, for developing applications. IaaS, infrastructure as a service, gives you access to fundamental infrastructure like servers and networking over the internet. Now, serverless computing is a concept that evolves from this model. Serverless doesn't mean there are no servers, it means you don't have to manage them. The cloud provider automates physical servers, virtual machines, scaling, and maintenance. In a serverless environment, developers can focus purely on writing code without worrying about infrastructure management. Let's look at the key benefits of the system we are building. First, it is serverless and event-driven. This means servers don't need to run 24/7. They only run when an event occurs, which significantly reduces fixed costs and maintenance overhead. Second, by offloading infrastructure management to AWS, you don't have to deal with a complex server maintenance. This allows you to focus on coding, resulting in much faster development speed. Next, we will prepare the AWS environment. Here, I will introduce how to create an account and the tools used. First, let's talk about the tools. AWS provides three fundamental interfaces for managing its services: the Management Console, the CLI, and the SDK. The Management Console, or the console, is a graphical, web-based interface for managing services. It's the main dashboard you use to access all services after creating an account. The CLI, command line interface, is a tool to manage services from a terminal. It uses an access key and a secret access key for authentication. AWS also offers a Cloud Shell, a browser-based CLI in the console that requires no local installation or setup. The SDK, Software Development Kit, is used to integrate services directly into your applications. AWS provides language-specific SDKs such as Python, Go, with libraries for making API calls from your code. Like the CLI, SDKs use an access key and a secret access key for authentication. This is a step to create a root account and IAM user. First, create a new AWS account and then set up IAM user. IAM is a service that manages permission of users in AWS. First, search AWS in your browser and go to the AWS web page. You will see a button in the upper right corner that says Sign into the console and click it. If you already have an account, you can sign in from this page. To create a new account, click Create a new AWS account. Enter your email address to authenticate your email. A verification email will then be sent to that email address. Next, enter your personal information such as address, credit card, phone number, etc. A credit card or debit card is required for your billing, even if your billing is zero. If you are not belong to a corporation and use AWS for personal development or just learning, I recommend you to choose the basic plan, which is free of charge. For developer plan and the business plan, you can get support from AWS customer engineers. Once you have completed this process, AWS account will be created successfully. This is a page called Management Console. And this will be the main page when you use the AWS resources from now on. Now I'm going to configure IAM. The first account that created is called a root user, and it will be a powerful account like administrator with access to your credit card. If the account is compromised, there is a security risk. Therefore, AWS recommends that you create an IAM user and sign in as an IAM user instead of using a root user normally. First, type IAM in the search window above and move to IAM's dashboard. And this is the IAM dashboard. In the initial state, root user has MFA is marked with a red triangle. It is recommended that you install the token apps on your smart device, and next time you sign in as a root user, authenticate with MFA. Next, create an IAM user. The next time you sign in as usual, sign in as this IAM user. You should not sign in as the root user except when checking your credit account. Click on User in the left menu, then Add User. Set the username. Check the access key and the password field for the credential type. The access key is used for the API, CLI, and SDK, and the password is used to sign in to the management console. Select Attach Existing Policies directly and choose Administrator Access. This will give the IAM user all privileges except credit card access. The tags can be any text you like. Tags allow identification of IAM users. If you create multiple users in the future, you may set the tags to identify each user. After successfully creating a user, be sure to save the access key and the passwords that are displayed. You can also download this in CSV format. When you have done set up IAM, you will return to the console again, and I will briefly introduce you to the structure of the screen. From the menu bar above, you can move to the various management screens. You can return to the top page by clicking AWS logo on your left. Click on Services to see all the services offered by AWS by category. You can also register frequently used services as favorites. Click on the CLI logo to open CrowdShell. By doing so, you can manage the command line from within your browser as well. Click on the bell mark to view various notifications. You can find out about events, changes, and incidents for the services you are operating. Click on the question logo to get support. The type of support available depends on the plan. For example, the basic plan allows ticket-based questions about fees, while technical support is available with paid plans. By clicking on the gear-shaped logo, you can edit the language, the visual mode, and so on. This is a recently added feature. The menu bar configuration may change in the future. Next, click on the pull-down where the region name is listed to navigate to the AWS region. Northern Virginia is selected by default. Basically, by selecting a region that is close to where you want to deploy your services, you can access your resources with low latency. Also, the services deployed and the fees vary slightly by region. Since AWS is a US company, so releases are generally the earliest in the US region and are then after rolled out to other regions. Documentation and other information is also available in English for the latest services and is gradually being translated into other languages. Finally, you can check the account information you have created from the upper right corner of the console screen. Clicking on an organization will take you to the AWS Organization Service page, where you can view information about the organization you belong to. From here, you can also check your service quota and the usage status and so on. If you need to access credit information, you will need to sign out of your IAM user and sign in as the root user. Next, we move to Section 2, Fundamental of Logistics Operation and the Key Technical Concepts. In this section, I will introduce the core concepts required for this system: location data, geofencing, and the MQTT protocol. Let's start with the location data. First, locations on Earth are represented by latitude and longitude. Think of latitude as the y-axis, representing north and south. The equator is defined as 0 degrees. Moving towards the North Pole, it increases to 90 degrees north. Conversely, 90 degrees south is the South Pole. Longitude is the x-axis, representing east and west. The prime meridian at the Greenwich Observatory in the UK is defined as 0 degrees. By combining these two values, we can uniquely identify any point on Earth. The GPS accuracy of modern vehicles is within a few meters. This is precise enough to meet the requirements for geofencing. In programming, it is common to use the GeoJSON format to represent the location data. Geo stands for geographic, and JSON stands for JavaScript Object Notation. JSON is a standard data interchange format used to structure data using brackets. For example, here is a GeoJSON sample representing the location of the central part of Tokyo. There is one critical point you must remember. In services like Google Maps, coordinates are often written as a latitude, then longitude. However, in GeoJSON and many computer systems, the order is longitude, then latitude, essentially x, then y. If you reverse this order in your code, your location will appear in a completely different part of the world, so please be careful. Next, let's clarify the difference between tracking and tracing. Tracking means following a target moving forward in time. It focuses on the present location and predicting future events, such as when will it arrive. In the supply chain, this is used for ETA, estimated time of arrival, and delay prediction. Tracing is retrospective. It means looking back at the history. It is used to investigate past routes or identify the cause of accidents. The system we are building today focuses on tracking. We will grasp the truck's current location to predict its arrival. Finally, let's talk about the last 1 mile. Literally, this refers to the final mile, or about 1.6 kilometers. In the supply chain, it refers to the final leg of the journey to the destination. Goods travel from manufacturers to distribution centers and warehouses before reaching the customer. Transport between major hubs uses highways and flows relatively smoothly. However, the last 1 mile involves delivering to specific homes or factories. Unlike highways, local roads are narrow and complex. Drivers also have to handle tasks like unloading, operating forklifts, and processing paperwork. Because this leg involves intricate tasks that are hard to automate with self-driving tech, the last mile is considered the biggest bottleneck in logistics. Therefore, automatically notifying the receiver when the truck is within a certain radius so they can prepare for unloading is a high-value solution in the field. Next, let's talk about geofencing. A geofence is a virtual boundary set on a digital map. Using location data like a GPS, the system automatically detects when a device enters or exits a specific area. The biggest advantage is that you don't need physical sensors or gates. It is cost-effective and you can easily change the boundaries via the web. While the concept was developed at the University of Missouri in 2004, it became widely practical in the 2000s with the global spread of smartphones and GPS technology. Let's look at some use cases. The most common use is setting a fence around a warehouse to detect arrivals in advance. If staff start preparing after the truck arrives, the driver has to wait. By using geofencing, staff can clear the loading dock, prepare forklifts, and handle paperwork before the truck gets there. This technology is often used for automatic check-in in dock scheduling systems. It is also used for risk management, such as detecting entry into restricted areas or alerting when a vehicle deviates from its assigned route. Geofencing works by detecting the exact moment a device crosses the boundary. It triggers an event when a device enters or exits. This allows us to track both when a truck arrives at the facility and when it departs. Technically, the relationship between the geofence and the tracker is determined by math. We calculate the distance between the center point of the geofence and the tracker's current latitude and longitude. If that distance is smaller than the geofence's radius, the tracker is considered inside. By using Amazon Location Service, AWS handles these geospatial calculations automatically. This means you don't have to write complex mathematical formulas in your code, allowing you to save significant development effort. Next, let's talk about MQTT. MQTT is a communication protocol that runs on top of the TCP and IP stack. Its defining characteristic is that it is extremely lightweight, making it the standard for message exchange between sensors and devices in the IoT world. Here is a comparison table between HTTP and MQTT. While HTTP is the standard technology for the web, MQTT is designed for IoT. HTTP follows a synchronous request-response model. In contrast, MQTT uses a pub-sub model, which is asynchronous and decoupled. The biggest difference is efficiency. IoT devices operate in environments like a car or factories where network connections aren't always stable. If we used HTTP, the long header information, like destination and source details, would create high communication costs and frequent errors. Therefore, we need a lightweight communication model that minimizes data overhead. Let's compare the data structure of HTTP and MQTT. HTTP packets contain a lot of header information, such as methods, version, destination, source, and content type. This results in high communication overhead. On the other hand, MQTT manages data in binary, not text. This means there are no unnecessary new lines or spaces, and the header can be as small as just 2 bytes. Next, let's look at the communication models. In HTTP, the client sends a request and the server sends back a response. If the server is down or the network is congested, you get an error. And this is a synchronous process. MQTT uses the pub-sub model. We call the sender the publisher and the receiver the subscriber. This is an asynchronous model where the publisher and the subscriber do not connect directly. Instead, a broker sits in the middle. In our case, AWS IoT Core acts as this broker. Because MQTT is asynchronous, it allows for decoupling. The truck can keep sending data without knowing who is receiving it. Also, a single message sent by a truck can be received simultaneously by multiple systems, like a map app and an analytics app. This lightweight, asynchronous nature is preferred for IoT because devices often move at high speeds or operate in areas with poor connectivity, like tunnels or mountains. Finally, let's explain topics. Think of a topic as a routing label or an address. The topics are generated dynamically when you send a message, so you don't need to predefine them. They follow a hierarchical tree structure, similar to folders on your computer. On the subscriber side, you can specify this hierarchy to receive a group of data at once. For example, you could subscribe to a topics that let you receive data from all trucks currently in Tokyo. Moving on to section 3. In this section, we will build the actual location infrastructure using Amazon Location Service. Amazon Location Service is a fully managed geospatial service provided by AWS. Simply put, think of it as AWS's equivalent to the Google Maps platform. It allows you to create maps and process geospatial data like latitude and longitude. In this course, in addition to the map itself, we will use two key resources, trackers and geofence corrections. The tracker receives location updates from IoT Core and stores the history of positions. The geofence manages virtual boundaries, like a 500-meter radius around the warehouse, and automatically evaluates whether a tracker has entered or exited the area. Traditionally, implementing this logic required complex coding. However, Amazon Location Service handles all of this management for us, allowing us to focus on building the application. For this demonstration, as shown in this diagram, I will create a rectangular geofence around the Union Station in Washington, D.C. Once created, we will associate our tracker to this geofence correction so they can work together. In this section, we will implement the Amazon Location Service. We are going to create the three types of the resource: the geofence, the corrections, maps, and the trackers. As I mentioned earlier, the Amazon Location Service became general available in 2021. This is a relatively new service. The console UI changed frequently, so I will demonstrate two methods: how to create a resource using the management console and how to use the command line, the CLI via the Cloud Shell. First, let's start with the console. So search for the location. So you can find the Amazon Location Service and click the service icon. On the landing page, you will see the Try It section where you can test the maps, the geofence, and the trackers. So let's clicking on the maps, and since I am in the US East 1 region, North Virginia region, and it will display the Washington DC, and you can change the map style, for example, the satellites and the imaginary. Okay, let's go back to clicking on the location service again, and scrolling down to next to the Try It of the geofence. And here, you can try drawing the geofence, and you can use your mouse to draw the circular geofence. Okay, clicking on the Draw Geofence and choose the circle, and clicking on the around the specific area, and like a park, then you can use and you can use the simulate tracker feature, and you can simulate the tracker moving on the map like this, the tracker moving on, and then the tracker going into the geofence, and it triggers the enter event, and conversely, if you move it out, and you can see it triggers an exit event. So we will recreate this behavior programmatically later in this course. So now let's create on the actual resources. Go to the location service again and open the menu bar on your left hand, and you can find the manage resources section and clicking on the maps places. Okay, and from here we are gonna create the new map. Click on the create map. Okay, and this time the folder name we're gonna set the logistics map, and we will leave the settings as default and using the S3 navigation style, scrolling down to clicking on the create on the map. And now you can see the map has been created. So clicking on the geofence in the left menu, clicking on the create geofence collection, and this time name it with the logistics, the geofence collections, and click on the geofence collection. Okay, and once created, and we need to register the actual geofence area. Clicking on the out geofence. So, and in this hands-on, we will define the polygon around the Union Station in Washington, D.C. And this is the actual GeoJSON file with the Union Station of the Washington, D.C. And you can find the coordinate with the x-axis and the y-axis and in the script. So we're going to upload this file to the Amazon location service. Okay, I have uploaded the GeoJSON coordinates file in the location service, and clicking on the add geofence. Okay, you can find the geofence is added successfully here. So next is the trackers. Clicking on the trackers on your left menu bar, and moving on to the creation page of the tracker. So clicking on the create tracker. Okay, this time, and I'm going to name it the deliver tracker, and leaves the position filtering setting as default, the accuracy based filtering. Scrolling down to the bottom and clicking on the create tracker. Okay, so the tracker is soon immediately created. So next we need to link the tracker to the geofence, and this is the most critical step. We need to associate the tracker with the geofence collection, and without this association, the system won't detect if the tracker enters or exits the area. So on the tracker's detail page, look at the link geofence collection sections, and clicking on the link geofence collection, and select the logistic geofence collection we just created, and then click on the link. Okay, that covers the manual setup of these sections. However, since the console UI might change, I also want to show you how to execute this using the command line, and this is often faster and more reliable. Clicking on the cloud shell icon, the terminal symbol in the navigation bar to open the terminal. And we will use the script to set the variable, the region, and account ID, and run the AWS CLI commands to create all the resources at once. And if you have already created resources with the same name in the console, the script might return the error saying they already exist. And firstly, let's define the basic configuration, and we set the region to US East 1, the North Virginia, and automatically fetch your AWS account ID. And I'm going to paste the command and the clicking on the enter. Then I'm going to set the variable region equal to US East 1 for my case. And on the same way, the account ID, this command will get the account ID of mine, and clicking on the enter. And next, I'm going to set the map name equals logistics map. I have already created the logistic map, so I need to change to logistic map 2, for example, and clicking on the enter. And on the same way, the logistic geofence collection and number 2, same way with the tracker name with delivery tracker and number 2, because we have already the delivery tracker logistic geofence collection already. And then clicking on the enter. Okay, and next we create the map resource, and we are using the create map command, and I'm going to copy and paste the command. And here we specify the vector S3 navigation for my map, so clicking on the enter. Okay, and the next we're going to create the geofence collection, and I'm going to copy and paste the command directory here, and think of this as the container that holds our geofence rules. Clicking on, and now we registered the specific geofence area, and we defined a rectangular area around the Union Station using the polygon geometry, and copy and paste the latitude and longitude directory here. Scroll it down and enter. So next we create the tracker and copy and paste on the same way. Okay, and this resource acts as a digital shadow of a delivery truck receiving the location update. Okay, and finally, most importantly, we must link the tracker to the geofence. So again, I'm gonna copy and paste the command, and click on the enter. Okay, and you can find all the resources is created, and going back to the console, you can find the logistic map number 2, and you can find the geofence collection number 2, and again the track number 2. Okay, that's all for the explanation of the Amazon location service. Let's move on to section 4. In this section, we'll set up AWS IoT Core. IoT Core is a managed cloud service that enables secure and scalable communication between IoT devices and cloud applications. It uses protocols like MQTT and HTTPS to exchange messages within a strictly encrypted environment, significantly reducing the risk of interception. It is also fully scalable. This means that whether you have 10 devices or a million, AWS automatically handles the infrastructure. You don't need to manage any servers. Essentially, IoT Core acts as a central hub that ingests the messages from millions of devices and routes them to other services. IoT Core connects devices to services, but security is paramount. We don't want every device accessing every service. To maintain security, we need to strictly control which device sends data to which service. Here, we need to understand two concepts: authentication and authorization. Authentication is verifying who the device is. Authorization is determining what action that authenticated device is allowed to perform. In IoT Core, we use keys and certificates for authentication. and policies for authorization. To register a device in IoT Core, you need to download a private key and a certificate. The private key is a secret file stored on the device. It contains the cryptographic data used to sign messages. The device certificate acts like a digital ID card. It contains information such as the expiration date, issuer, and the public key. Together, they guarantee authenticity, ensuring the device is genuine and not an imposter. Think of the certificate as a passport and the private key as your personal handwritten signature that only you can produce. Standard websites typically use one-way authentication. For example, you verify that you are connected to Amazon.com, but Amazon doesn't necessarily verify your device initially. However, IoT Core uses mutual authentication. First, the device verifies AWS using a root CA. This confirms that the server is actually AWS and not a fake site. Second, AWS verifies the device using the client certificate we just discussed. They check each other to ensure a trusted connection. Next, let's look at policies. A policy is a JSON document that defines the permissions for an authenticated device. The IoT policy controls what the device can do within IoT Core. For example, you can restrict a device so it can only connect with a specific track ID or only publish to a specific topic. Note that this is different from an IAM policy. An IoT policy is for devices, while an IAM policy is for users and services. Like your administrator account, we will manage these separately. Finally, let's introduce the rules engine. The rules engine allows you to route data sent from devices to other services based on specific criteria. In this course, we will set up a rule to forward data to the Amazon Location Service Tracker. Rules are defined using SQL-like syntax. In our hands-on lab, we will use select all to grab all the data, including latitude and longitude. While we won't use it this time, you can also use a where clause to filter data based on specific conditions. The hands-on for setting the AWS IoT Core. From the AWS Management Console home, let's configure the IoT Core. The first, search for the IoT and select the IoT Core. And this will take you to the IoT Core dashboard where we can manage the devices and the rules. The first, let's create the rules to handle the incoming data. So from the left side menu bar, you can find the message routing. Clicking on the message routing and clicking on to the rule. And first click on the create a rule. This time, we're going to name the rule as logistics location rule and then click on next. So from the SQL statement, they keep the SQL version as the recommended latest version. And in the SQL statement box, we're going to type the select from the logistic/tracking, and we will use this topic name logistic/tracking later in our Python simulator. Scrolling down and clicking on the next. And then configuring the rule actions, configure select the Amazon location service from the list location, and you can find the location data to Amazon Location Service Tracker, and choose this one. And you will be asked to input the service details. The first, the tracker name. Select the tracker name, delivery tracker, and we create the area. And the device ID, we're gonna put the the device ID and the latitude. We're going to put the LAT and the longitude and the LON and the timestamp value with the timestamp and with the timestamp unit with the seconds. Okay, and the syntax dynamically pulls the value from the JSON data sent by the IoT device. So they're clicking on the next IAM role. Okay, for the IAM role, clicking on the create a new IAM role, and the name is something like the IoT, the rule location role, and clicking on the create. Okay, I already have this one, so you're gonna change the name to, for example, the IoT rule location role number 1, and click on the create. And then, okay, the permission will be configured automatically. Clicking on the next and then review the details and scrolling down to the bottom and click on the create to finish the setting of the rule. Okay, next let's register the IoT device. On the same way, from the left menu, you can find the all device and the things, and click on the create things. Select the create a single things and clicking on the next. And this time, the name the things with the delivery truck 01, and we will match this name in our Python code later. And leave the other settings as default and clicking on the next. Okay, and for the device certificate, choose the auto-generate a new certificate recommended, and clicking on the next. Okay, and skip on the policy attachment for now, and clicking on the create things. Okay, you will see the download page. Please download the device certificate, the public key, and the private key to your computer, and we will rename and use these files in the next chapter. And once downloaded, clicking on the done. Okay, let's confirm the delivery truck 01 has been created, and also go to the security and click on the certificate to verify. Okay, to verify that the status of the newly created certificate is now the active status. So now let's configure the security permission next. So go to the security, and you can find the policy to click on the create policy. The first name the policy as, this time, for example, my IoT device policy, and using on the builder to switch to the JSON and paste the permission code directly to here. I'm going to copy and paste the permission policy, and this policy allows the developer to connect, publish, and subscribe and receive the messages. So click on the create. Okay, and finally, we need to link this policy to the certificate we just created. Going back to the security and the certificate, and clicking on the certificate for the delivery trucks, and click the policy tab, and click on the attach policy, and select the my IoT device policy. Click on the attach policy. So this completes the AWS IoT core setup. And in the next chapter, we will configure the downloaded keys and the certificates to run the simulator. Next, we move to section 5, Python implementation, simulating delivery trucks. In this section, we will write the Python script and run a test to verify that data is being transmitted correctly. In this hands-on lab, we will use Python to generate location data, since installing physical IoT hardware on a real truck is time-consuming and complex. We will run our Python code in AWS Cloud Shell to simulate the device. Let's walk through the logic of the Python script. First, we load the route data, which consists of latitude and longitude, as an array. These coordinates are defined as floating point numbers. We also capture the current time to use as a timestamp. Next, we convert the route data into JSON format. The JSON payload includes the device ID, timestamp, latitude, and longitude. There is one important note regarding the timestamp. We use Unix time, also known as epoch time. Unix time is a 10-digit number representing the seconds elapsed since January 1st, 1970. Then, we send this JSON data to AWS IoT Core using the MQTT protocol. To mimic the movement of a real truck, we add the short wait time between sends. By repeating this process in a loop, we simulate the virtual truck moving continuously along its route. For reference, we will be using the Python SDK. This is the official library provided by AWS. Normally, implementing MQTT communication from scratch is very difficult. You would have to manually code the TCP and IP connection, the TLS encryption handshake, packet assembly, and the keep alive signals. By using the SDK, we can abstract all this complexity into just a few lines of function calls. AWS provides various libraries like this to help developers implement complex logic easily and securely. So moving on to the Python configuration and simulation. Now we are in the Cloud Shell page, and from the top of the menu bar, you can find the Cloud Shell, and then now we are in the Cloud Shell page. And first we need to install the Python SDK in our environment. In the Cloud Shell, I'm going to copy and paste the command, the pip install AWS IoT Python SDK, and clicking on to install the SDK. So next we will upload the certificate key and the file that you downloaded in the previous section. And in the top right corner, and you can find the action and select the upload file and select your certificate and the private key file to upload them. So, and then once the upload is complete, verify the file using the ls command, and you will see the file with the very long name, like the certificate.pem.crt and the private.pem.key. And we are going to make them easier to handle in our codes. Let's rename them using the mv command. In the first, the mv the certificate.pem.crt to cert.pem, clicking on the enter. And next, on the same way, the mv very long name with the private.pem.key file to private.key, and clicking on the enter. And lastly, the mv Amazon root ca1.pem to root-ca.crt, and clicking on the enter. Then again, we're going to confirm with the ls command, and you can find that the file name is changed from the very long name to the cert.pem, and the private.key and the root-ca and CRT. So next, now we need to get the AWS IoT endpoint, and you can find the endpoint in the IoT core, the console menu, and the setting on the domain configuration, and you can find the domain name here. This is the endpoint, and with the region name, for my case, US East 1 and Amazon AWS.com. Alternatively, you can give it via the command line by the AWS IoT to describe the endpoint and click on the enter. And then copy this endpoint URL, and we will need it for the Python script. This is the Python code we're going to use in this section, and let me briefly explain the code. Firstly, imports the AWS IoT MQTT client from the SDK, and the next, this is important, and you must replace the endpoint variable with the URL you just copied, and then scrolling down to the connection block, and this block configures the port 8883 and loads the 3 certificate file, the root.ca.crt, the cert.pem, and the private.key. And scrolling down to the loop bar, and this is the simulation logic. It defines the route from the White House to the Union Station in the Washington, D.C., and then sends the coordinate every 3 seconds. And I have uploaded the Python file from the action, the upload file, to confirm the LS to find the Python with the dc underscore and the sim.py, and this is a Python code. So now let's verify that file, and you should see let's run the script. I'm gonna copy and paste the command with the Python 3 and the dc underscore sim.py. Okay, so if successful, you will see the output saying the connected successfully, and followed by the sent with a JSON payload appearing every few seconds. And this means you simulate the truck is sending the location data. So let's verify that the data is actually reaching the AWS cloud. Going back to the AWS IoT and the core console, and from the left side menu, you see the MQTT test client. Okay, and in the top filter, enter the logistics / the tracking, the topic we defined in the code, and clicking on the subscribe. Okay, and then you should see the location message arriving in real time every 3 seconds. And this confirms that our Cloud Shell environment and AWS IoT core are connected via the MQTT protocol. So the unit test is successful, and return to the Cloud Shell and press the Ctrl+C to stop the Python script loop. Let's move on to section 6. So far, we have built the backend components using IoT Core and Amazon Location Service. In this section, we will implement the front end, the website itself, to visualize our map. We will cover 3 main topics: hosting a static website on Amazon S3, implementing authentication and authorization using Amazon Cognito, and walking through the actual build process of the site. Let's look at the system architecture. We are building a website that displays map information to the user. First, let me introduce the core service for this, Amazon S3. Amazon S3 is the most versatile object storage service provided by AWS. In S3, the container where we store files is called a bucket. It offers high durability and virtually unlimited capacity. You don't need to provision storage size in advance. You simply pay for what you use under a pay-as-you-go model. It ensures redundancy by automatically replicating objects across multiple availability zones, which are physically separated locations. S3 covers a wide range of use cases from storing logs and backups to data lakes. In this hands-on lab, we will use it for static website hosting to serve the HTML and JavaScript for our map. Let me explain what a static website is. Simply put, a static website displays fixed content to the user. It does not perform any internal processing on the server side. In our case, it just delivers the files needed to display the map. The opposite is a dynamic website. Dynamic sites process requests internally, often involving databases or complex calculations. There is a difference in infrastructure. Dynamic sites require computing services like EC2 to handle the logic. Static sites only need a storage service like S3 to deliver files. Because they don't require a running server, static websites are generally much more cost-effective. To display the map, we will use an open-source library called MapLibre. MapLibre offers highly customizable mapping capabilities. It is optimized for rendering maps from Amazon Location Service, making it the perfect choice for our project. For reference, here is a comparison between MapLibre and Google Maps. Google Maps is an all-in-one package. It includes proprietary map data, store information, street view, and routing. While it has high brand recognition and quality, it tends to be more expensive. Also, it has strict terms of service regarding how you can use the data. While you can use Google Maps with AWS, it requires separate billing management via a Google Cloud account. Therefore, we will use the open-source MapLibre. Amazon Location Service recommends MapLibre as the standard library. In fact, Amazon itself is a major sponsor of the MapLibre project and actively supports its development. Next, we will cover Amazon Cognito, authentication and authorization. This section includes permission settings. This is a common stumbling block for beginners, so let's go through it carefully. Amazon Cognito is a service that provides secure user authentication and management for web and mobile apps. It supports sign up, sign in, an identity store, and ID federation. The identity store is where user credentials are managed. In Cognito, this is called a user pool. ID federation is a mechanism that allows you to use external social identity providers to grant access to resources. Here is a diagram showing the standard authentication and authorization process using an identity provider, IDP, and the service provider, SP. The client requests access to the service provider. The service provider redirects the user to the IDP. The user sends the credentials like ID and password to the IDP. At this stage, optional multi-factor authentication may be required. If authentication is successful, the IDP generates an assertion. An assertion contains the information about the user and their permissions. This is typically provided in SIAM-L or OpenID Connect formats. The IDP sends the assertion to the SP, and the client is redirected back to the SP. The SP verifies the assertion and grants access to the client. While this flow is technical, understanding this underlying logic is crucial for real-world implementation. Let's look at the general use cases for Cognito. Cognito handles both authentication and authorization. You use the Cognito user pool to issue tokens for authentication. You use the Cognito identity pool to grant authorized access to specific resources. You can also link it with third-party IDP. Let's break down the components, user pools and identity pools. The Cognito user pool acts as your identity provider. It handles standard features like storing usernames and passwords, password recovery, and token-based authentication. It can also trigger other services upon sign-up or sign-in events. The Cognito identity pool is used to grant authorization to authenticated users to access resources. Think of the user pool as the authentication foundation and the identity pool as the authorization foundation. Or Identity and Access Management is a service that manages access permissions for resources and the accounts that access them. With IAM, you can control fine-grained access, which enhances security across your environment. When you create an account, a root user is created, but typically you sign in as an IAM user. An IAM user has specific permissions to perform certain actions on specific resources. IAM also allows you to set permission on the resources as well as users, and this allows for security designs such as the law of least privilege. Here are the core elements of IAM: policies, users, groups, and roles. An IAM policy is a JSON document that defines permissions, what actions are allowed on which resources. You control access by attaching these policies to users, groups, or resources. There are two main types of policies: identity-based and resource-based. The identity is the actor performing the action. In this hands-on, this refers to the user accessing the system. The resource is the target. In this case, it's the S3 bucket hosting our website. You need to attach a permission policy to the identity. In our lab, we will attach an IAM role to the user authenticated via Cognito via the internet. This role will have a policy allowing access to the website and the Amazon location service. For S3, we attach a bucket policy, which is a resource-based policy to allow read access. As a side note, if the identity and resource are in different AWS accounts, you must explicitly grant permission on both the identity-based policy and the resource-based policy. This is a common gotcha even for experienced AWS users. Since we are using a single account today, strictly speaking, we don't need explicit permission on both sides for S3 access, but we will configure it for clarity. Our website embeds map data from Amazon Location Service into the index file on S3. Therefore, the IAM user requires permission to access the Amazon Location Service map. Here is the IAM policy we will grant to the user. Technically, we are granting a specific IAM role named the Logistics Map Guest role to the guest user authenticated by Cognito. We attach the policy to this role. The actions starting with geo represent permissions for Amazon Location Service. Next is the policy we attach to the S3 bucket. Here, we configure public access to allow arbitrary GET requests from the internet. GET means read-only access. In other words, users can view the files but cannot write, modify, or delete any objects in the bucket. Finally, let me briefly explain SIG4, Signature version 4. Every HTTP request sent to the AWS environment undergoes an internal signing process. For example, when sending a request from your local environment, a signature is generated using the date, region, service name, a request payload, and the metadata. This signature is added to the header to ensure the request is secure. When using the CLI, SDK, or Terraform, this header generation happens automatically. It's managed, so you typically don't need to worry about it. For context, version 4 has been the standard since 2013. upgrading incrementally since AWS launched in 2006. Compared to older versions, it supports more services and includes more request elements in the signing process for enhanced security. So let's get started hands-on from the AWS console, and we're going to set up the front end, the Cognite, S3, and the visualization. So first now let's implement the front end, and we need to configure the authentication service, search for the Cognito, and the moving on to the Amazon Cognito's dashboard. And open the left side menu bar and select the identity pool. And we will create the new identity pool. Click on the create identity pool. Select the guest access this time, which allows the unauthenticated identity, and click on the next. And this allow our public access to the AWS resources without requiring the user to log in. And for the IAM role settings, select the create a new IAM role. And the name will be, for example, logistics, the identity pool, and role. And we will edit this permission later, and clicking on the click next. Okay. And name the identity pool, this time logistics identity pool, and leave the other setting as default. Click on next and review our settings, and click on the create identity pool. So the once created, and you will see the identity pool ID. And please copy this ID now, and as we will need to paste it into our website code in the index.html file later. So next we need to grant permission for this identity pool to access Amazon location service. So go to the user access tab inside, and click on the user access tab. And you can find the logistic identity pool role here, clicking on, and you can navigate to the IAM role section. So we need to add a plus alpha policy to default one, and clicking on the permission tab, and then find the add permission, and dropping down on the right and select the create inline policy. And then I'm gonna copy and paste directory to here, moving on to the JSON editor, and I'm gonna copy and paste the JSON policy directory here and paste it. So the new policy includes the geo, the get map, and the get device position. And this policy allows action starting with the geo to retrieve map and the tracker data. And then click on the next. Okay. At this time, name the policy, for example, the logistics map policy, and click on the create policy. And verify that the policy is now attached here for the unauthenticated role. So going to the S3 next, search bar S3, and you can find the Amazon S3 icon here, and clicking on and go to the Amazon S3 page. So we're gonna make the new bucket. From your left side menu, you can find the general purpose bucket, and click on the create new bucket. And this time, we're gonna name the packet with, for example, logistics name demo and 2025, and with, for example, 1222. And please note that the packet name must be the globally unique name. Adding for example, the data or your name helps you ensure the uniqueness. Okay, and scrolling down to the block public access settings for this packet, uncheck the block all public access. Check the box to acknowledge the warning, and the turning off the block public access might result in this packet being public. So scrolling down to click on the create packet. Okay, and next open the new logistic demo packet you just created, and go to the property tabs, and scrolling all the way down to the bottom, and then you can find the static website hosting. Click on the edit on static website hosting and select the enable. And for the index document, type the index.html and click on the quick save changes. Okay. And scrolling down to the bottom again, and you can see the Backend website endpoint, a URL starting with the HTTP, and this is the URL we will access later. And then next go to the permissions tab to add the Backend policy that allow public read access. Scrolling down to the Backend policy and click on the edit. And then I'm going to copy and paste the Backend policy's JSON code directly here. And I'm going to change the Backend ARN to the logistic demo, the 2025, the 1222 to here in the resource sections. Okay. This principal is set to the asterisk and any, the meaning that anyone can read the file, which means the get object means the read the file. So clicking on the save changes. Okay, and then going back to the Backend and the logistic demo, the 2025. So let me briefly explain the index.html file we are about to upload. And in the scripts section, you can see the identity pool ID, and please paste the cognate identity pool ID you copied earlier here. And for reference, the const map name and the tracker name, ensure these matches the resources and we create in the section 3. And scrolling down to the transform request, and this function handles the signature version 4, the signing process required to securely request the AWS map data. And scrolling down to, you can find the function initialize the MapLibre's map centered on the Union Station, and then it draws the blue circle marker representing the truck, and using the set interval, it fetches the device position from the Amazon location service every 3 seconds and updates the marker's location. So going back to the S3's console, in the Object tab, click on the Upload, and I have added the index.html file. And once uploaded, going back to the Properties tab, and scrolling down to the bottom to click on the static website. Okay, it might take the moment to load, but you should see the map of the Washington DC will be displayed, and right here. And then at this point, the blue card marker, the static, because the Python script isn't running. And then we're gonna going back to the cloud shell and run the Python simulator again, and going to the and the cloud shell, and I'm gonna move the run the Python, the DC underscore the sim.py, and clicking on. So, and you should see the coordinates updating every 3 seconds in the terminal. So going back to your browser, the map, so you can find okay, and now you see the blue marker, the moving on the map from the White House to the Union Station in the Washington DC. So it is entering the Union Station area. So this completes the visualization hands-on. And then next we will build the logic to send an email notification when the truck actually enters the Union Station geofence. Nextly, we move to section 7. In this section, we'll introduce our final goal, the automated notification feature. First, I will introduce the concept of event-driven architecture and the related services. Then, we will integrate all the components we've built so far to run the final system test. In this section, we focus on the notification logic. We will use two specific services, Amazon EventBridge and Amazon SNS. First, let's talk about event-driven architecture. In this hands-on lab, we want to detect the exact moment the truck enters the geofence. Once the location trigger is detected, we will send an email notification to the user. An event-driven architecture is a design paradigm where actions are triggered by specific events. For example, it detects the moment a truck enters a geofence, or when server CPU usage exceeds a predefined threshold, and immediately triggers the next action. On the other hand, polling is where the system periodically checks the status, for example, checking the truck's location every 60 seconds. Because event-driven systems actively push information from the source, they offer much higher real-time performance compared to polling. Amazon EventBridge is a serverless event bus service provided by AWS. It receives events from AWS services or third-party applications and filters them as needed and allows them to specific targets. EventBridge plays a central role in building event-driven architectures. By decoupling event sources from targets, it improves the system flexibility, scalability, and resilience. In this lab, we will use the Event Bus feature. It will detect the tracker enter the geofence event and trigger an email. In EventBridge, you can define an event pattern. This defines which resource and what type of event to listen for. In our case, we will configure it to detect the enter event from the Amazon Location Service geofence collection. Finally, let's introduce Amazon SNS. Amazon SNS is a fully managed pub/sub messaging service. It allows you to push lightweight messages, like mobile push notifications, to a large number of subscribers. However, note that it's not suitable for rich text or two-way communication. It supports various protocols to cover a wide range of needs and integrates seamlessly with other AWS services. Pricing is fully pay-as-you-go and is extremely cost-effective for sending millions of messages. It is commonly used for use cases like sending push notifications to millions of users or monitoring vast fleets of IoT devices. Let's start hands-on for setting up the notification logic with Amazon SNS and EventBridge. The first, let's set up the notification service. From the console home, search for the SNS and navigate to the simple notification service. Okay, and we will start by creating a new topic from your left side menu bar or you're on the top of the dashboard. You can find the create topic. Okay, and this time we're going to choose the standard and not the FIFO. And for the name, enter, for example, this time the logistic notification topic, and you can use the same name for the display name, and leave the rest as default, and click on the create topic. Okay, and then now we need to create the subscription to receive the messages from this topic. Click the create the subscription, and then for the protocol, this time we're going to choose the email, and in the endpoint field enter the valid email address. For my case, I'm going to set the temporary email address here, and then click on the create subscription. And then you will receive the confirmation email from the AWS. Please check your inbox and click the confirm subscription. And once confirmed, and you will redirect to the subscription confirmed page in your browser. And this step is required to receive the notification. So next, let's set up the Amazon EventBridge to trigger notification. Go back to the console and input EventBridge and go to the EventBridge page. Okay, so we're gonna set the EventBridge trigger the notification. Okay, select the rules from your left side menu bar. Okay, and keep the default settings, the rule with the event pattern, and create the new rule. So we will define the rule this time. We're going to set the name with the logistics arrival rule, and click on the next. Okay, I have already this one, so I'm going to change the name with number 1. Okay, and now we define the event pattern. The scrolling down to the event pattern. Okay, and for the AWS services, select the Amazon location service, type location service, and then for event type, select the geofence, enter, and you will see the JSON pattern generated on the right. But we want to be more specific, so click on the edit pattern and replace the content with a JSON. I'm going to copy and paste directly. And this configuration filter the event so it only triggers when the event type is enter, and it happened within our specific logistic geofence collections. And in real-world production scenario, you might have the multiple geofence collection, and this filtering ensures the notifications are sent only for the specific collection we are interested in. So scrolling down to the bottom and click on the next. And the next, we're gonna configure the target, and we want to send this event to our SNS topic. Select the AWS service and choose the SNS topic, and choose the logistic notification topic we created earlier, and Let's choose the create a new role for the IAM role, and click on next. And we don't use the tags, and you're gonna go to the text, and finally review your settings on the review page, and click on the create a rule. So we have now completed the setup. So next, let's proceed to the final test to see if everything works together. This is the final integration test. Let's execute the final test from the Cloud shell and run the Python script again, the Python 3 dc_sim.py. So as we have been before, the latitude and the longitude data is being sent continuously. And let's switch to the S3, the map page, and you can see that the blue marker is moving every 3 seconds. And we have a geofence set up around the Union Station, and once the markers enter this area, the EventBridge will trigger and email notification will be sent via the SNS. And going to the console page of the AWS IoT, in your left MQTT test client, and just to be sure, and if we look at the MQTT test client, and then we can see that location data is arriving successfully. And then going to the verify the backend trigger, and go to the EventBridge rule we created, and open the monitoring tab, and shorten the time resolution, for example, the 15 minutes. Okay, and you can see the data point in the invocation graph, and this indicates that the rule was triggered successfully. And finally, check your email inbox. You should have received a notification saying the truck was entered the area. So this confirms our entire system, from the IoT device to the map and the notification, is working correctly. And then let's go back to the Cloud shell, and then stop the Python script, Ctrl+C. Okay, this concludes the integration test. Finally, we have reached Chapter 8, Conclusion and Next Steps. In this final section, we will review what we have learned throughout the course and discuss ideas for advanced implementation. First, we started by discussing the global landscape of supply chain digitalization. We then implemented fleet management, a key pillar of this digitalization, by building a working prototype using a simple simulator. We implemented the entire system on the AWS cloud. We utilized modern services like IoT Core and Amazon Location Service, alongside popular foundational services like S3, Cognito, and EventBridge to build a complete workflow. We also learned how to integrate these services securely using IAM policies. By building a complete data flow rather than just studying services in isolation, I hope you gained a solid understanding of how to architect a real-world system. We also covered key modern cloud concepts, serverless, and event-driven architecture. By leveraging these technologies, we can automate processes with the minimal human intervention. And by using fully managed services, we can offload the operational burden to AWS, allowing us to focus on development